Okay, this is questions on quantum physics. Now this picture here is a artistic representation of a photon being a quantum of electromagnetic energy. Now its nature is such that it has both a particulate nature, as in it's one unit, one discrete quantity of energy, alongside a wave-like nature indicated by these undulating sort of wavelengths, I suppose. So the idea is it's both a wave and a particle. Okay, question 1. An electron is accelerated by a potential difference of 1500 volts in a vacuum. What wavelength does the electron have? Now, one of the cornerstone equations is the de Broglie relationship, Planck's constant over the momentum. We think of a photon having both a momentum and a wavelength. So that's the wave-particle duality idea encapsulated in the one equation. Now we need to calculate the momentum, and to get the momentum, of course, we need to know the velocity. So mass times velocity, we need to find the velocity. That, of course, can be found if we know the accelerating potential difference, in this case 1500 volts. As we've seen in the charged particle topic, if we equate the kinetic energy to the work done on the electron by the electric field with a potential difference of 1500 volts, we can generate this equation and find the velocity gained. So we plug in the values. The mass of the electron is used in the bottom line, the charge of the electron on the top line, and the voltage 1500 volts. That gives us 2.297 million, or megameters per second. That's times 10 to the power of 6. So now we can calculate the wavelength, just multiplying this velocity by the mass of the electron. We get the momentum of the electron, and then divide the Planck's constant h, which is 6.63 times 10 to the power of negative 34, by the momentum we calculate. Now if you do this properly, we should get a wavelength of 317 times 10 to the power of negative 12 meters, in other words, picometers, where 1 picometer is times 10 to the negative 12 of a meter. Okay, question 2. The electron has mass m and kinetic energy E, gained from an accelerating potential difference V. Show that the de Broglie wavelength lambda of this electron is given by the following relationship. So that's what we have to show. Now you can see, hopefully, a couple of things here. This bottom line looks a lot like the kinetic energy relationship when we're trying to find velocity from a potential difference. Not quite the same, of course. It sort of gives you a clue as to how to proceed. So one of the ideas is to simply start with that concept that we're trying to find V, and let's say it's V squared. So half mv squared equals the kinetic energy. So if we rearrange and make V squared the subject, it's going to be 2 times the kinetic energy divided by the mass. And since we don't have the capital E in this equation, we need to find an equation to substitute for capital E, kinetic energy. Of course, we know this is equal to work done by the accelerating potential which will be EV. So we can substitute EV for capital E in that equation there. So you get 2EV over M. Now, momentum, as you know, is mv, and that means momentum squared is m squared v squared. So now we can substitute v squared equals 2ev over m, this thing, into here, and obtain 2mev for P, momentum. So there's a couple of steps there which I've combined into one, but hopefully you can follow the logic. Of course, now it's pretty obvious that we can write, since we know the de Broglie relationship to be h over momentum, the final step is simply to substitute in for momentum. Oops, I forgot the square root sign there, that's why it's confusing myself. Sorry about that. There we go. Now that's the correct thing there.